Hello, everyone. Thank you for joining. My name is Patrick Berus, and I'm the head of communications at Instrat. Together with me, we have Patrick Kubicek, our chief modeler at our organization. We'll just give ourselves 1 more minute for other participants to join, and then we will start. Hello to everyone joining. We'll give ourselves a couple more seconds before we start. I want to give the space to all the participants to join us. Okay, I think we're good to go. Welcome everyone. Once again, my name is Patrick Berus. I am the head of communications at Instrat. Together with me, the webinar will be led by Patrick Kubicek, who is the project lead for PIPESA PL, our tool for modeling the Polish energy transition. Today we meet to participate in our webinar called "Will the Grid Be an Energy Transition Bottleneck?" And to those of you who are maybe not as familiar with our organization as our Polish counterparts, I'm just going to say that Instrat is a Warsaw-based think tank with a mission of supercharging policies and public opinion with open data and research for a fair, green, and the digital economy. Okay, a couple of technicalities. During this session, you can participate in our Q&A session, which you can access by pressing the button in the module on the bottom of your screen. Please feel free to ask questions during the whole webinar, and we will have some time at the end of the webinar to address those, and Patrick will answer those. Also, this webinar is recorded and will be available at our YouTube channel later on. Without further ado, I give the floor to Patrick. Please.
Thanks, Patrick. Good morning to everyone. I'm so happy to see so many of you. It's kind of like tradition nowadays, like to host these PIPESA PL webinars. I think we meet for the third time with me as a speaker. So let me share my screen. Yeah, I hope it's visible. So today we are meeting to talk a little bit about the new edition of the energy modeling project at Instrat, which is dedicated to grids. And as Patrick mentioned, Instrat is a Warsaw-based think tank with strong technological foundations. We run our own energy platform. We develop our own tools like PIPESA PL models, and this is something that really distinguishes us. And using these tools that we develop and the data we gather and share, we really try to influence public policies, evaluate public policies in Poland, because we believe that, well, the topic I'm focused on, the energy transition, the strategy in this field must be based on sound analytical foundation. And what we need in this field is definitely more transparency and no more black box analysis. So these are questions that will whose answers will shape the future of our energy system, which is the backbone of the whole society. And we really need to ensure that the decisions we make are based on arguments that we all know what stands behind them. That's why we really stand for this open access, and all the modeling project we do in Instrat is based on this principle. All our data we use for the models themselves, they are made publicly available so that anyone can scrutinize them. So the topic of today is, will the grid be an energy transition bottleneck? So this is like the topic for this year's edition of Instrat's modeling project. And why did we choose this topic? Well, in the public debate in Poland, there are like several estimates how much like the grid expansion will cost in the next years. So you hear like numbers ranging from 200 to 300 billion PLN until 2040, or like even some years ago, there was like in an official document, we saw like a number 500 billion. Okay, so these are huge numbers from just like looking at this like as a human. And so they sound large, and when people hear them, sometimes they think, okay, maybe the energy transition based on renewable energy sources might not be as cost efficient as it is usually portrayed. But is it really the case? Like I believe many investments will happen anyhow, as much of grid infrastructure in Poland is quite like the relative age of infrastructure is old, so it needs modernization anyhow. And I think the real question we should be asking is, what is the relationship between like the level of the scale of renewable energy deployment and an additional grid expansion cost that we might have to carry. I also believe that we should not also like calculate this grid expansion cost as like the final step after we know, okay, what energy sources we need. Now let's discuss how we will make sure the grids can facilitate that. I believe from the very start, we should jointly optimize the expansion of generation, storage, consumption infrastructure, as well as the distribution and transmission grids. Because only then can we be sure that like we find this sweet spot between like too much and too little grid investment. And this is obviously a big task, a very challenging task, for which we need more complex tools than we have at our disposal now. And this is exactly what our modeling project this year is about. We at least want to make a first step towards creation of such a tool for Poland. Such tools exist, obviously, like especially at European scale, like we all know PIPESA-UR. But like at national scale, I would say this kind of models, which somehow try to optimize grid expansion costs, are still rare, and well, at least in the Polish context, I don't know any model like this, especially open one. So the agenda for today is I will make a short recap of what we have done in Instrat Energy Modeling Project so far. Then I will discuss a little bit how we plan to include grids in our new version of the model. Then there will be a short demo of which will already take into account some grid costs. And then there will be space for your questions. So this is something like we are really proud of in Instrat. This is PIPESA-PL, which I already mentioned. It's like an open model of the Polish energy system, which is like heavily inspired by PIPESA-UR. So at the moment, the model includes not only power sector. Yeah, I mean, the focus I made in the introduction is like on the power sectors, on the power grids. But we should like see the big picture, like, and see all other sectors integrated with the power sector. And this is what we already have in our model. We have electricity, heating, both district and decentralized, mobility in the sector of light vehicles like electric cars, and hydrogen sectors. So this is like a simplified view of all the technologies. We have the model. And I already mentioned this model is publicly available. You can check like the most current version, still without grids, at GitHub. So the model answers the question, how can we like satisfy demand for all these energy carriers, electricity, heat, mobility, hydrogen, at the lowest cost? And by this, I mean both the operational costs of running the system at each hour of the year, but also optimal investments in a new infrastructure that will be needed. And PipesAPL is like a very important tool for our work at Instrat. Like there are at least 4 Instrat papers that are like heavily based on the results of modeling, where we describe in detail all the assumptions we make for our like energy scenarios, and we like answer pressing policy issues. So in the series of these papers, we answered questions whether it makes economic sense to accelerate RES deployment. Well, the answer is yes. We show benefits of sectoral integration, and also we addressed like important issues of the flexibility of the Polish power system, both from supply level and demand. So if you are interested, like I encourage you to look at our publication. And I will also mention like there are other publications that like are supported by the energy modeling results, like for example the future of lignite mining in Poland, where we'll really like discuss in detail, based on PipesAPL results, what are the perspectives for this sector. So this is like the main result from our last publication. This is like we call it the main scenario of the energy transition, which is like an ambitious pathway until 2050 that Poland would have to take to reach climate neutrality and like be compliant with the European goals for climate action in the field of energy. And not only this, because like we really have that is called climate neutrality here. So as you see, like well, by 2024 we ended in Poland with like around 30% of renewable electricity. We will most likely exceed it this year. And in our like ambitious scenario, under like ambitious policies, regulations that enable a fast renewable deployment, Poland could reach as much as like 60% of renewable electricity by 2030, and even up to 80% in 2040. In this picture, I also show you like the numbers from the most current draft of the Polish NECP. And as you see, like the trend is very similar to what we proposed in our report. And I mean, that's a big change, yeah, because like the Polish government has never officially considered the possibility of exceeding like 50% of renewable electricity at any year of energy transition. And now we see like even in 2030, like the draft version of NECP, Polish NECP, sees this level being exceeded. So I'm happy to see like this convergence of our scenarios, like with the scenarios that officially are declared by the government. And if you want to learn more about our scenario, I encourage you to look at our data portal, Energy Instrat PL, where now we have a dedicated section to our PipesAPL scenarios. And what I want to focus now is like the fact that like we really model the system hour by hour. So we model all this variability of the renewable energy, which I think is one really has to capture this in a model, like to make like credible statements about like whether renewable energy can really have this high share in the Polish power system. And what we should be aware of, like by 2040, we will see like a big increase in the volume of electricity consumed in Poland. But it's not only that, like the maximum power load, so like the maximum electricity production at a given time will increase even more, exactly because of this variable nature of renewable energy sources. Well, I mean, wind and solar, and especially solar has this high variability, like, and we have to find ways to deal with this huge load. Yeah. So in our scenario for 2040, we could see even up to 75 gigawatts maximum load in the system, when today, like, the system is like ready to deal with, let's say, 30 gigawatts. And I mean, that's obviously a challenge for the grids, and we did not take grids into account in our model so far. And as you see, for example, in the moments of big peaks in PV generation, we also have peaks in hydrogen production for electrolyzers, charging of batteries. And one can make like argument that if we build electrolyzers or batteries at the location of renewable energy installations, the grid will not see this whole 75 gigawatts, which will allow us to save some money on like grid expansion. But let's say, okay, these were some qualitative arguments, and now we really want to make it more quantitative. Which brings me to the next section, where I will discuss exactly what we are planning to do in this year's edition of the project. If there is like any questions during my presentation, please put it in Q&A, and maybe after this section, before I move like to this demonstration, I will try to answer like the most pressing ones, like to make sure that we are on the same page. So what are the goals of the project this year, and what like research questions we would like to answer? So first of all, like we really want to know, like, to what extent do the expansion costs of transmission and distribution grids scale with the deployment of renewable energy sources? Like, what is the relationship? Like, we don't want just to have like one single number. We really want to know, okay, if we decide to build more renewable electricity, how much will it cost us in terms of grids? But still in this remembering that this should be somehow a jointly optimized problem. We want to know, like, how do those grid costs will affect the economic viability of renewable electricity sources? Because so far we kind of assumed this will not change the picture too much. What will be the new optimal generation mix? So will we still keep this 80% of share of electricity, renewable electricity, or maybe it will be a bit less? A very important aspect is how can we reduce those costs related to grid expansion, because we know that we can achieve big reduction of costs through like smarter use and design of energy infrastructure. Already now in Polish regulation, it is possible to like have shared connections of wind and solar, for example, cable pooling solutions, which definitely saves on the spending on grid infrastructure. We should maybe think whether at some point it will be better to orient PV panels in east-west rather than south, such that like the profile of PV generation is like more friendly for the grids, even if it comes at the cost of like some, let's say, reduced potential of solar PV production. And really want to know like what conclusions can be drawn from like co-optimizing all these types of infrastructure at once. So then maybe we can learn what kind of savings we get if we locate electrolyzers located next to renewable energy installations. Or maybe instead we should still be building them next to hydrogen demand centers, because like we would have to transport this hydrogen anyhow. Well, we will not cover the hydrogen grid in this project, so we cannot fully answer this question, but at least we can try to address it. And also, like, very interesting question one could ask is about prosumer energy. Do really rooftop solar PV does it have potential, like, to save on grid expansion costs? Many studies say it is the case, so we really want to see whether we have similar results here. So now I will get a bit more technical and discuss in detail how we attempt to represent the grids in the new version of PIPES-PL model. So first of all, I have to say it's a very challenging task. So like the computational complexity of an optimization problem, which has like such a high temporal resolution, like 8,760 hours, all hours of a year, combined with this investment optimization. So we not only model the operation of the system, we also want to know which infrastructure to build. This is very computationally expensive already now. So for sure, we will not be able to model each power line in Poland separately. We have to somehow have a similar approach as modeling the generation infrastructure, where, for example, so far we treated all power plants of a given type as like a single aggregate unit. So this kind of similar approach we'll have to take to grid infrastructure. So we have to think of like some reasonable components of grids that we can split grids into and then aggregate them. And obviously, like, we have to go away with this copper plate assumption, like that the electricity generated in the north of Poland can always flow to the south. And I mean, also we have to find some like sweet spot between nice granular representation and what the model will be able to handle, and also which data we have. So that's why we decided to split like Poland geographically into 16 areas, which correspond to provinces, województwa, voivodeships, and like it's like a good choice because also we can find data on what energy infrastructure or energy demand is in each of the regions. So what we'll do, we will like aggregate all this generation, storage, distribution grids at the level of provinces. And what we will have between provinces will be like the transmission capacities, which will represent in an aggregate manner the actual transmission lines that we have in the Polish power system. And so yes, this is like a simplification of the grid problem, but it still improves a lot on what we had so far in PIPES-PL model, which was basically a copper plate model. So the diagram on the right shows you like an example of a focus centered on like one province of Poland, where we show like all these transmission distribution grid levels. So we decide to split like the infrastructure by the voltage level. So we have extra high voltage, which correspond to transmission grid. And as I said, we will model each of the lines, each transmission capacity between two provinces, which is like aggregate transmission lines. And also, like, we know that the systemic thermal power plants fired by coal and gas, they are connected usually to this extra high voltage. So let me just jump to let's keep the focus on the transmission grids. So on the left, you see the structure of the transmission network in the Polish power system as of now. So we do with some procedure, which is like inspired by some US National Transmission Planning study. With this procedure, we kind of reduce this big complex picture into less complex picture, like to be able to do any calculation. And this method basically boils down, I mean, at the end, it turns out that the transmission capacity we see between provinces is more or less equal to the summed transmission capacities of all the lines connecting several provinces. So I think it's a very similar approach to PIPES-EU. So like we have this 16 nodes of the system, and 16 provinces, and for each province we have their own power plants, their own electricity demand, and as I said, we compile various sources to inform the model. Okay, so this is like transmission grid. This is pretty standard, what we also find in the PIPESA EUR. The distribution part is a little bit less standard because we increased the complexity compared like to PIPESA EUR, where you just have some kind of one distribution grid component which represents all the grid infrastructure. In the Polish context, I think it's important like to have more divisions. So we have like high and medium voltage level and low voltage level. And we believe it's important to have those two separately because most of the wind and solar installation in Poland, they are connected at high and medium voltage level. And even in our representation, they will have their own dedicated node because I believe most installations of this type, they are installed far away from the existing grid infrastructure. So like you will need to build these connections, which is like important cost category. But also with this design of our representation, we are able to see the benefits of cable pooling because this capacity that you see, which is named variable res connection, this can be to some extent shared between wind and solar. And at the low voltage, obviously we have the prosumer PV as the generation source, which can play and already plays in Poland a very important role. And also at this low voltage level, we will see a lot of heat pumps installed at households, which is like a source of load to the system. And I think it's like this. So this is still a simplified picture that you are seeing, but I think it will be able to like, will help us answer all these questions, or at least many of the questions that I proposed. For example, now we can think, okay, where do we want to install batteries? Do we want them like at the demand load location, or maybe we should install them exactly where wind and solar is generated, which will allow us to save on grid costs. Electrolyzers, do we want to have them at like wind and solar location, or do we want to have them like at this general load location, which is where industrial consumers are located? So I'm really happy to hear what you think about this in the Q&A session. What's very important is, okay, we have all these components which are kind of abstract, and how do we put costs on them? Yeah, because like we know maybe how much an AC line costs, but how can we know how much distribution costs, and like what is even a good unit to measure this distribution? So before I jump into this, I will just make a short summary of what are data sources of grid costs now in Poland. So we have reports of the Polish Power Transmission Distribution Association, which provide like financial summary of each year of the grid operators in Poland, transmission and distribution. And overall, the annual grid expenditures annually in Poland are around 10 billion PLN, which 8.7 is on the distribution, 1.3 is on transmission. So you see like distribution is way more costly, and like we can also expect most of the costs will be in the distribution sector. And we know that in the distribution sector, around half of these current expenditures are related to new investments. The rest is like operations and maintenance. There is like a very famous document in Poland, which is Charter for the Efficient Transformation of Poland's Power Distribution Networks, which was signed by the Energy Regulatory Agency together with distribution system operators. And they have like this charter includes like a scenario of spending we would have to take in the next 8 years, or I mean until 2030. And this would the investments described there is around 13 billion PLN annually. So compared to the number I showed you before, we know like half of it is investment. This would mean a threefold increase on year investments. Okay, so we can already assume we will have to spend more. But what we also learned from this document is that only approximately 12% of these costs are for direct grid reinforcements necessary to facilitate connections of renewable energy sources, energy storage, electromobility. So there are many, it seems like much of the investment will have to happen anyhow, like new customer connections, maybe data centers, like this is a big source of new energy demand. And also replacing overhead lines with cables because it generally increases the reliability, which we want to have anyhow, whether we have renewable electricity or not. In this transmission sector, like the most important document is probably the network development plan by the Polish TSO. So the investment in the transmission sector would translate into around 5 billion PLN annually, which is also like a big increase from the current situation. It's worth mentioning that this number includes the costs of the north-south high voltage DC line, which seems to be very costly. So we will try also like to address this issue in our modeling, but if this line is really as costly as we hear from some media news, probably the model will not recommend it. But let's see further in the project what results we get. And also like to get some like unit investment costs indicators. One interesting data source is Acer. And they published like a document which is like a summary, like the averages of grid investments that were done in the last years in Europe. So from this we can learn more or less how much it costs to build one AC line or how much a transformer costs. So this is also very important in this cost calibration. So now I will show you maybe like without going maybe too much in detail, maybe if later there are questions, I will go back. But you see like this procedure of calibrating cost is very time consuming and one really has to do it in careful manner, like to make sure like the final results are robust and are based on and provide numbers that we can trust to some extent. So in the transmission sector, the components we will have is this transmission lines, this aggregate transmission line. So here we believe like the number that is more than Acer reference unit cost probably better represents the current situation in Poland. The same goes for transformation capacity, like from the extra high voltage to high voltage, because it's not only the transformers that costs, but also the whole substation. So we calibrate this cost assumption in a way to somehow be able to reproduce this current grid costs in Poland as reported. So we have to make certain assumptions. Okay, so how much maybe operation and maintenance costs? We assume it's 1.5% of the investment costs. We also have kind of assume like how much new infrastructure is built at the moment to know like, okay, how many investments were financed. So we kind of try to carefully calibrate this. These are preliminary numbers, but those numbers, like in our opinion, coincide with this number of 1.3 billion expenditure on transmission grid costs in Poland nowadays. In the distribution sector, we have like more kinds of components. So we have this general distribution at high and middle voltage levels. We have the connection of variable electricity. We have the transformation between medium voltage and low voltage, and we have distribution at low voltage level. And like the unit to measure these costs in is, I call it megawatts equivalent, which is more or less like the peak energy flow that these components have to deal with, which is kind of intuitively understandable. Like the higher your peak load in the distribution grid, the more grid you need, the more you have to pay for it. So we also like try to calibrate these assumptions in a careful manner. also trying to make sure, like, okay, the unit costs are probably higher in the low voltage sector because these are low voltages, many small devices. So the unit cost will be higher than in the high and medium voltage. Probably variable renewable energy connections nowadays there is not really much cable pooling, so probably they just equaled the summed capacity of wind and solar. And so we really tried to look at all of this at the same time to come up with some reasonable numbers, and those numbers we believe also probably represent to some extent well the current expenditure of distribution grids. So this was the most technical part. I will just quickly go into demonstration of some preliminary results, but maybe now I will make this short pause as I promised and see what questions we might have, and maybe I can quickly answer them.
Yes, we have a couple already, so they're in the panel. So I just 4 of them, so I will just answer them now. So Frank is asking about the numbers in the opening. Do they include development of storage capacity and hydrogen infrastructure? As far as I understand, these are only grid costs. So these are really lines, transformers, substations. So my answer is no. So there is no like energy storage capacity included or hydrogen infrastructure. And it's just all about power grids also. Maybe this was not clear. I really do not address the question of like hydrogen grids or heat networks, which is also a very important issue, but we just focus on the power grids now. Charging infrastructure. I believe, yeah, I mean, in a way that this cost probably include like the expenditure, like to deliver power to EV chargers, for example, I don't know, along highways. But I mean, there are no costs of the charger itself, right? It's because this is not really something that belongs to the grid system operators. Okay, the next question: how does our model account for the fact should run and be planned for based on the n1-1 principle? Yes, so the principle says that even if one element of your system drops out, the system has to remain stable. And we kind of apply this at the transmission level. So we do it by setting just like an upper cap of a load of an AC line. So I think at the moment we are capping it at 65%. So we do not allow the model to plan the operation of the system such that at any time any single line has more load than 65%. It just has to account for the fact that we need some safety margin. Like we do not model it in pipes PL, but in real life it can always happen. One line will go out and then other lines will have to take this load. So there always has to be the safety margin. We chose the 65% based on some literature review, but also the procedure of this grid reduction I showed you. There you can explicitly model this n-1 principle, and from this you can also get estimate, okay, how much on average you would need to reduce the load on the lines, and that's how we came up with the 65%. Question about embedded solar generation. I'm not sure I know what embedded solar generation is, so maybe if you could like elaborate on this question, and I will come back to it later. Another maybe question from Chris. What are the main principle of technical envelope you apply in the model? Yeah, I think I just discussed this. 65%. And also like at the level of approximation we are using, what we model is only active power flows, so there are no reactive power flows. And this also means that, yeah, you have to keep some extra capacity for this reactive power, because the capacity is measured in megavolt amperes, not in megawatts. Yeah. And Jan's question, do you have hourly demand data for each individual region of Poland? No, we don't. We would like to have it.
So at the moment, we just use the same profile for each region, for each province. We will think internally whether we should add some variation on top of it, but unfortunately, such data is not available. All right, so let's move on to the final section, after which there will be a time for proper Q&A. So what I will show is just some demonstrations, so please do not get attached to the results too much. This is just to show what kind of outputs we can expect from the model. This is all based on very preliminary assumptions. The model is also not fully ready to answer real questions, but still I think it's interesting to see what we can do at the moment. So first of all, we need to do some baseline simulations of the Polish energy system, because we only through this procedure we kind of know what are the required what are, like, let's say, maximum power flows through all these distribution components that I showed you, because that's something we don't really have data on, and even if we had data, it's kind of hard to make like connection with the model. So like the best way probably is to see, okay, like let's assume that the system now is able to handle the current electricity demand given the generation sources we have. So this is probably what we have now. So this is the starting point. And on top of it, if we want to have more power flows, we'll have to pay more money for expanding distribution grids. So for this, like, it's really important to have this good baseline. And we do this by simulating the energy system as it is now. And like on the left-hand side, you have like a map of Poland with the provinces, with all these nodes. The upper half circle is the structure of electricity generation, and the color codes are as described in the picture on the right. So for example, green is wind, pink is solar PV. And on the bottom, we have like the structure of the electricity demand, and most of it is gray, which is kind of like base demand. We also have a little bit of red, which is like power to heat, existing heat pumps or resistive heaters. We also have a little bit of yellow, which is this is a new thing, because now we model grid losses like as a result of the model, not really assumption. Okay, like the percentage loss is still assumption, but the actual loss is, and the losses are different components, so it's like a non-trivial issue now, what kind of losses we will have in the model. So this is the yellow on the bottom. Between the nodes, we have lines, these transmission capacities. So the thicker it is, it means the more capacity it has. And the more red it is, it means on average, it's more heavily loaded. So at the moment, you see the most heavily loaded, at least as a result of our model, I don't know if it's reality, is the line between central province of Poland, Łódź, and Silesia in the south. And in the Łódź region, we have like this big Bełchatów lignite power plant. And it seems like it's an important source of electricity for Silesia, and Silesia, on the other hand, is like a big electricity demand center. And on the right side, you see like what were the installed capacities in the Polish power system by the end of 2030, 2023. We don't know the future yet. So you see like Polish power system by 2023 had almost 10 gigawatts of wind and around 17 gigawatts of solar PV. Well, we haven't updated the model yet to 2024, but now it's even more. It's over 10 gigawatts in wind and 20 gigawatts in solar. So this is like the baseline simulation. And now let's maybe ask some interesting question. What would be the optimal level of wind and solar batteries if we could add them to the current system without any limitation? Well, only the cost is the limitation. We want to have like optimal system costs. And in this variant, I do not add this grid cost. So all this discussed is not existent here. So this is like as we did it for the last 2 years in Instrat. So the answer is yeah, we should add a lot of wind, like around 13 gigawatts, because that's very cost efficient for the system. And if we add so much wind, probably we do not need so much PV. We still need a little bit more. But under this assumption that we can add as much wind as we can, we should really add wind, not solar PV at the moment. Interestingly, like in this situation, the model says the optimal curtailment of renewable energy sources, so like the losses, like something the system cannot absorb, while in the simulation, the baseline simulation was 2%. In this case, it can be even 13%. But I don't think we should be thinking of it as losses, because I mean that's what the model shows as cost optimal. So yeah, there will be some losses at certain hours, but overall, this volume of cheap electricity from wind is very beneficial for the system. Okay, but this is when we had the like no grid constraints really at distribution level. What if we add this cost, as I discussed them, these numbers, how will it change the optimization problem? And it turns out it changes. So in the previous example, we had like optimal addition of 13 gigawatts of wind. If we include all these costs, now we get optimal addition, which is 12 gigawatts. So there is difference. It's not a big difference, but it's notable. Yeah. So definitely that's something that improves the robustness of the model. Interestingly, of all these kinds of distribution capacities I showed you, only the connection of variable renewable energy was expanded. Well, it's understandable because we add wind at this node, so it needs more connection with the rest. But interestingly, no other components were expanded, which means probably it was not cost efficient to do so, but still the system could, in principle, absorb this amount of wind energy. So this is the preliminary results. So we will have this kind of maps showing this approximate flows, average flows in the system. We will have like the electricity generation mixes per each province. So we will see probably a lot of wind, also wind offshore in the north of Poland being transmitted to the south of Poland, which is like a big area of demand. But what I showed you, it's this kind of the webinar last year was about it. It's PIPESA-PL mini, which means like we only have 4 weeks, not the whole year. It's because like this problem has become much more computationally expensive by adding all these provinces, grids. So when testing the model now, we'll really limit ourselves to 4 weeks. I'm not sure we will be able to reach the whole year. We need to see how the computational complexity, how much time that we have to spend on our computers will scale with adding extra weeks. So maybe we will end up at like 12 weeks, I don't know. But please remember, this is just a pilot application of our method, and we should not draw too much conclusion of it. And with this, I would like to summarize and provide some conclusions of the webinar today. So grid expansion and operation maintenance costs are missing in many optimization-based models of national energy systems, which definitely is the case for Poland. We intend to include them in the new version of our tool. It is, though, challenging to represent transmission distribution grids in energy models. Well, that's why it's not done frequently, and it requires a very careful calibration of cost assumptions. And when we do incorporate grid costs in the optimization problem, it will most likely lead to changes in the optimal energy mix. Maybe we will have a little bit of less of variable renewable electricity, but I don't want to draw too much conclusion at this point. I think there's like a lot of analysis to be made. And finally, you see, I spoke a little bit about the details, and I hope I convinced you these details matter, are important, and there are such details behind every energy model. So I believe it's very important, like, to be able to interpret the results well we really need to have access to the data behind the model and the model itself. So that's why I plead again for open source and open access principles in energy modeling. And now it's time for your questions. And please also, if you have like any idea for some interesting research questions we could address, or if you just want to comment on our methods, please just write in the chat, or it's even possible to speak if you want. Okay. So at the moment, I will just have a look at the questions we have still unanswered. I just put my email address and the email address of Michał Smoleń, who is the head of Energy and Climate Program. If you have any questions that you might want to get answered after the webinar, please also get in touch with us. And I'm now looking into Q&A. Probably.
We have two questions in the Q&A session.
Yeah. With the new government in Germany, ministers are pushing in one direction, reopening shuttered nuclear, favoring gas plant with carbon capture and disposal, and industry is pushing in another direction, hydrogen, with no preference for green and blue. Do you see a similar dynamic in Poland? That's a very interesting question. Well, I think there is a general agreement in the society, in the government. There is like a need for nuclear power plants. Regarding gas, I believe the ministry might be not so fond of this idea, but like the transmission system operator is really pushing for it. And I believe, like, I think even in the government it changed, because probably, we will have like an extra capacity market auction just for the gas power plants, because in the previous capacity market auction, basically most of the money went to battery systems. And I mean, that's a bit problematic, yeah, because like even we showed in the last report in November last year that for these periods of Dunkelflaute, the batteries probably do not help you so much, because they can only store energy for like a certain period, definitely not week or 2 weeks. So I think now there is like increased understanding also in the government that, yeah, we need this gas-fired power plants. There is also hope that they will be powered by biomethane in some future. So like a climate-friendly, more climate-friendly fuel. Regarding hydrogen, I think this is something that is heavily discussed now. Like even Instrat is like has its own project on like steel factories, steel production, whether it should be powered by exactly green hydrogen or blue hydrogen or biomethane. And I think like it's a very interesting period now in Poland regarding this discussion about industry, about which fuels should industry use. And I don't think like either industry or government has a very clear position on this. But we will see how the situation unfolds in the next months and years. Chris, will the grid be an energy transition bottleneck? Yeah, I mean, I cannot really answer this question right now. Because we are just starting and we don't have the results. But yeah, my intuition is that no, because I mean, we also did some calculation. Okay, these big numbers, even if they were such big, how do they compare to the like operational and investment costs in like generation, storage, and so on? And those costs are bigger. Yeah, we have to spend more money on new generation infrastructure. At the moment, we spend a lot on operations of the system by purchasing fuels. So when you really sum up those numbers, this grid expansion costs are not something that would become the bottleneck of the whole energy transition. But I think really there is a case for making it smart. Yeah, there is like a big potential to avoid unnecessary grid reinforcements, and that's what we will try to focus on in this project. And Michał Zabłocki, in the variant B, I saw very little storage in the places of wind energy production. What is the reason of placing it farther from production? Okay, maybe I go back to this slide. R&D. Okay, first of all, storage is not visible, probably not at all, because at the moment, the capacity of like the main storage technology, which is pumped hydro storage, this light blue color, it's probably so tiny that you can't see it on the left. But I mean, it's a very good comment, yeah, to observe that even though we allowed the model to build battery systems, it did not choose to do so. And I believe it is because at the moment, because as you see, like this is kind of 2023 situation. So the starting point is 2023 with all the costs. And like we asked the question, if I had a magical wand and I could build immediately a lot of wind and solar and batteries, how much should I do it to make it cost optimal? So because of this high costs of battery storage, the optimal addition is 0 at the moment. It simply is so that it's cheaper to lose this electricity, this 13% of renewable electricity. It's cheaper to lose it rather than invest in batteries that could, okay, they would help to minimize the loss, but it will come with too high system costs to do it. But it's not the full story, because the battery costs are decreasing by 2030. Certainly they will be lower. Batteries also play other roles in the system than those we model. They can provide regulation services, frequency regulation. They make the grid stable. What now is done by coal-fired power plants or gas-fired power plants, in future it will be able, even now battery have technical capacities to do it, and this will be a new source of revenues for the system. So I'm pretty sure we will see more batteries than our model will tell us it is optimal to do. And I see one more question from Chris. Thanks for being an active participant. The question is, did you get an estimate of the network capacity and cost needed to enable the capacity development envisaged in the latest network development plan by the Polish TSO? It says, I mentioned this number, it's around 60 billion by 2034. So this corresponds to this 5 billion annually number. And we will definitely try to compare what our model shows is like optimal transmission grid development. We will try to compare it to the plans of the Polish TSO, like in some aggregate manner, because it's a very important question. A lot of investments of TSO are in the region of Gdańsk, which is like the northern one, because like it's the location of the first nuclear power plant, and also the first stage of the Polish wind offshore capacities will exactly be connected to the same region. So we'll have like one point which will have to transmit all this, absorb and transmit this electricity from nuclear power plant and wind offshore. So like already now, like there are a lot of ongoing projects of AC lines to strengthen this north-south corridor. But yeah, as from some media news, we know that like just this south-north corridor, if it's done at high voltage DC technology, it could cost even 30 billion PLN. Yeah, so just half of all the investments of the TSO for the next 10 years could be due to one cable. That's very expensive. But maybe needed. I don't know yet at this point.
We have one
Chris,
more.
again.
Yeah, we have one more question from Chris, but then after that, I think we need to finish.
All right. So if there are any last minute questions, please put them in the chat. If not, I will just answer this last question. Do you publish how much megawatts, megavolt amps of transmission distribution network needs to be built? Yeah, I mean, we will try to definitely, I mean, we will make all the data public. So if you want like technical details of this megawatts or megavolt amperes, for sure you will find it. When we publish things, we always have to limit ourselves like to most important figures and numbers. And if we believe this will be like important number that people will be able to relate to, then yeah, definitely we will do it. Yeah, thanks for your feedback, Chris. So Chris is mentioning that this kind of modeling is done in US and Australia. Well, I don't know about Australia, but I really looked at this US study, which really inspired me to do similar stuff.
Okay, it's already past noon, so I think we need to finish now. Thank you, Patrick. Thanks a lot for leading us through this webinar and interesting findings. Thanks to all the participants. Just to state the obvious, the recording of this webinar is going to be available on our YouTube channel. And you already have contacts for Patrick and Michał. And if you want to contact me, you have any even technical questions or something outside of this subject, you can find it on our website. And we thank you for your attention and see you soon.
See you. Thank you.
Thank you. Bye.